Imagine standing next to this massive steel wall. Right. And it is just radiating heat because there's a 1500 degrees Celsius inferno happening right inside it.
Oh yeah, it's practically a contained volcano.
Exactly. And beneath your feet, the whole floor is vibrating. You've got these massive feed pumps forcing chemically altered water into pipes at like 225 bar of pressure.
Which is an unimaginable amount of force.
Right. And then above you, there's this high-speed obstacle course of titanium blades spinning at exactly 3,000 revolutions per minute, just howling like a jet engine.
It's a remarkably violent environment.
It is. And that sheer, violent, chaotic, physical reality is what you are actually interacting with every single time you lazily reach out and flick a light switch in your living room.
We really do take that instantaneous connection completely for granted.
We totally do. Welcome to the deep dive, by the way. Today, our mission is to look at the machines on the other end of that wire, because they aren't just batteries. They're basically multi-story chemical and mechanical beasts.
Yeah, today we are unpacking an incredibly dense electrical engineering textbook chapter, and it focuses entirely on thermal power plants, specifically steam power plants.
And we are going to bypass all the heavy academic formatting, I promise. We want to extract the mind-blowing scale of this engineering.
Right, we're looking at the why behind their design. Like, why do we rely on these specific beasts? Why do they demand the fuels they do?
And why is the water circulating inside them chemically manipulated to the point where it would be a lethal substance if mishandled?
That is one of the most fascinating parts. But just to set the stage, the textbook lays out 4 main types of thermal plants generating power on the grid today.
Right. There's steam, simple gas, combined gas, and diesel.
Exactly. But if you look at the performance metrics, the steam plants are the absolute unquestioned behemoths of the group.
Oh, for sure. I mean, reading this, a single unit inside one of these facilities easily exceeds 600 megawatts of power production.
Yeah. They form the absolute backbone of the global electrical system. The capital expenditure to build just one of those 600 megawatt steam units is immense.
And they take up massive amounts of physical real estate, right?
Huge amounts. But they are favored because of their operational lifespan and really the remarkably low cost per megawatt over that lifespan.
Plus, they have this critical dual-purpose capability, especially in arid regions. They function as desalination plants, too.
Which fundamentally changes the economics of running them. But there is a massive drawback.
Okay, let's unpack this, because the textbook notes that despite that immense power output, it takes 5 to 7 hours just to connect one of these plants to the grid from a cold state.
Yep, 5 to 7 hours just to turn the machine on.
I was trying to visualize what dictates that lag time, and it feels similar to a massive freight train. You can't just throw a lever and expect thousands of tons of mass to jump from 0 to full speed.
That's a great analogy, actually.
It requires an incredible amount of time and energy just to overcome its own resting inertia.
Well, and it's also the physics of thermal expansion. A rapid startup would be catastrophic.
Because of the heat.
Exactly. If you just introduce 540 degree steam into cold steel turbines and piping, the outer layers of the metal expand way faster than the inner layers.
Oh, wow. So the metal would just tear itself apart?
Literally. The thermal stress would warp the turbine shafts and shear the blades right off the rotor. So it has to be brought up to temperature in painstakingly slow, methodical increments.
So because of that immense startup penalty, grid operators use them purely as baseload plants.
Right. They provide that steady underlying foundation of power that a region draws on day and night.
Which means they run constantly. I mean, you don't spool up a steam plant to handle the 5 p.m. spike when everyone gets home and turns on their air conditioning.
No, absolutely not.
Yeah.
You rely on fast-acting simple gas or hydro plants for those quick peak loads.
Steam plants just sit at the bottom of the stack, churning out massive volume without interruption.
And that continuous operation dictates where you can physically place them, too.
Right, you need massive heat sinks, like oceans or large rivers for cooling.
Yeah, and they need to be in close proximity to major industrial centers to minimize the line loss and infrastructure costs of long-distance transmission.
Makes sense. You can't build your massive freight train out in the desert and expect to efficiently ship its output thousands of miles.
Precisely. But because these baseload plants never sleep, their appetite for fuel is staggering.
The textbook gave some really intense statistics on what we are actually feeding these fires globally, and coal is still heavily dominating the mix.
It really is.
Like China is running coal for about 78% of its energy generation. India is at 59%. The U.S. hovers around 50%, and Britain relies on it for over a third.
But the text highlights some sharp contrast to that global average. It points to Egypt as this fascinating outlier.
Oh, yeah, where coal constitutes less than 1% of the energy mix, right? Sourced almost entirely from the Almagara mine in the Sinai Peninsula.
Exactly. And the reason for that global divergence and the overall shift away from coal in modernization efforts comes down to the emissions penalty.
The pollution is just wild. Producing a single gigawatt hour of electricity from a coal-fired plant emits 1,041 tons of CO2.
Yeah, 1,041 tons per gigawatt hour.
When you scale that up to a plant running 24/7 for decades, the atmospheric impact it's almost difficult to conceptualize.
It's massive. It makes sense that the reading notes this industry shift, with about 90% of newly modernized plants utilizing oil or natural gas instead.
Because gas provides a cleaner burn.
Right, and it avoids the massive logistical nightmare of physical coal yards. But you swap one extreme infrastructure for another.
Yeah, to feed a 600-megawatt plant, you are running massive 30-inch gas pipelines kept constantly at 20 bar of pressure.
It requires a continuous high-pressure river of explosive gas.
But here's the most counterintuitive element of burning all that fuel, whether it's coal, oil, or gas. It's the theoretical efficiency limit.
This is a tough one to grasp.
Despite the multi-billion-dollar infrastructure and all the precision engineering, the maximum theoretical efficiency of a modern steam plant sits at roughly 64.4%.
Yeah,
I really have to push back on that number because reading that was jarring. Are you telling me over a third of the energy potential in the fuel is just completely lost?
it is.
With all the metallurgical advances and computational fluid dynamics we have today, why haven't we engineered our way past a 64% limit? Are we just failing to capture the heat effectively?
What's fascinating here is that this is not a failure of human engineering. It is a hard, non-negotiable boundary imposed by the laws of thermodynamics.
So walk me through that.
Well, to generate power, heat must flow from a high-temperature source to a low-temperature sink. The textbook outlines the operational parameters.
Right. Steam leaves the boiler at around 550 degrees Celsius.
Yes, but eventually it must be cooled down to about 20 degrees Celsius to be pumped back into the boiler as a liquid.
Because pumping a gas against high pressure requires vastly more energy than pumping a liquid, so you have to collapse the steam back into water to maintain the cycle.
Exactly. And to achieve that phase change, you must reject the latent heat of the steam into the environment.
So you're intentionally dumping massive amounts of thermal energy into the condenser.
Yes, transferring it to the cooling water pulled from the ocean or river. Furthermore, the exhaust gases venting out of the chimney stack cannot physically transfer their remaining heat to anything hotter than themselves.
Oh, I see.
So they leave the plant carrying a massive amount of thermal energy straight into the atmosphere. The universe simply taxes the conversion of heat into mechanical work.
It's the cost of doing business with physics.
Very well put.
So since the engineers are handcuffed by that thermodynamic tax, they have to optimize every other variable in the plant with obsessive, almost microscopic precision.
And this is where the narrative shifts from roaring fires to aggressive chemistry.
Yes. The water circulating inside this high-pressure loop must be maintained at 99.5% purity.
Which is incredibly pure.
Yeah.
Introducing standard tap water or even heavily filtered river water into a 225 bar, 550 degrees system.
That's just a recipe for rapid self-destruction, right?
Completely. At those extreme velocities and temperatures, microscopic dissolved solids precipitate out and become abrasive projectiles.
Like the textbook details that catastrophic failure in an Egyptian power plant.
Yeah.
An entire steam unit was completely lost after just 1 year of operation.
One single year.
A machine built with heavy-gauge steel designed to run for decades, shredded from the inside out in 12 months just because of high salt and impurity levels in the feed water.
Yeah. The dissolved impurities strike the titanium turbine blades at supersonic speeds. It erodes the airfoil profiles and completely destroys the aerodynamic efficiency.
That is wild. So to prevent this, the water goes through a brutal, multi-stage chemical alteration.
Right. They start by pulling raw water from a river or sea, running it through physical screens to block the macro debris like fish, branches, mud.
But to strip out the dissolved invisible elements, they inject specific chemicals that force dissolved salts to react and coagulate into solid particles.
Which can then be physically filtered out.
But achieving 99.5% purity isn't enough. They then have to actively weaponize the water to protect the machinery. They add ammonia.
Right. The injection of ammonia pushes the water to an alkaline pH between 9 and 9.2.
And why that specific range?
Operating in that specific alkaline range chemically passivates the internal steel surfaces of the piping. It creates a protective oxide layer that drastically inhibits stray oxygen molecules from inducing deep pitting corrosion.
Wow. They also inject trisodium phosphate, which really blew my mind.
That's a crucial step.
Because when water boils, it leaves behind minerals that form scale on the heating surfaces. If scale builds up inside pipes carrying 1500-degree heat, it acts as an insulator.
Right. The heat can't transfer to the water.
Exactly. So the steel pipe absorbs all the thermal energy, overheats, and eventually bursts under the 225 bar of pressure.
It's a bomb waiting to happen.
But the trisodium phosphate forces those scaling minerals to form a soft, manageable sludge that can just be flushed out rather than a hard, insulating crust on the metal.
The water is meticulously chemically sculpted before it ever sees a flame.
Here's where it gets really interesting, though. Because this water purification process operates on such a massive industrial scale, it completely alters the fundamental utility of the power plant in certain regions.
Oh, absolutely.
The textbook points out that in Gulf countries, these facilities are not just spinning turbines. The sheer volume of ocean water they are distilling and purifying turns them into the primary source of municipal drinking water for the surrounding population.
If we connect this to the bigger picture, it explains the unique governmental structures in those regions.
It's like having a combined Ministry of Electricity and Water.
Exactly. The two resources are physically inseparable within this engineering loop. The freshwater isn't a separate industry. It is a direct byproduct of the power cycle.
And it's measured alongside megawatt output in massive units called MIGs, right? Million imperial gallons.
Heck, it's an incredible symbiosis.
So we've got our 1500-degree inferno fueled by high-pressure gas, and we have our 99.5% pure chemically armored water.
Right.
The actual generation of electricity is the violent mechanical collision of these two elements inside the boiler and the turbine.
Let's talk about that boiler. It's a standalone, heavily insulated structure that often reaches 3 stories in height.
Just massive.
And the interior furnace is maintained at that 1500 degrees Celsius by an array of up to 18 massive burners.
And to get the water into that environment, the plant utilizes those massive feed pumps to crush the water up to between 180 and 225 bar.
For context, 225 bar is pressure that would instantly crush most commercial submarines.
That is terrifying. And the plant usually runs 3 of these pumps in parallel, right? 2 powered mechanically by steam bled off from the cycle, and 1 massive electrical pump as a backup.
Yes, ensuring the boiler never runs dry while under fire, because if it did...
Total meltdown.
Exactly.
Yeah.
Once inside, the mixture hits the drum.
Right, the drum. That massive, heavily reinforced pressure vessel engineered to manage the phase change.
As the water boils, it creates a chaotic mixture of steam and liquid droplets. The drum utilizes a complex internal geometry of tilted plates and cyclonic separators to violently strip the heavy liquid droplets out of the vapor.
Because if a high-density droplet of liquid water makes it out of the drum and hits a turbine blade spinning at 3,000 RPM,
the kinetic impact would completely shatter the metal.
the drum ensures only pure, dry steam escapes. And the maintenance protocols for this thing are terrifying.
Oh, the manhole.
Yes, it features a literal manhole hatch so engineers can crawl inside the pressure vessel during downtime to inspect the separation plates.
Not for the claustrophobic. But before the feed water even reaches that high-pressure drum, the system aggressively scavenges its own waste heat.
Oh, to fight back against those thermodynamic efficiency limits we discussed earlier.
Exactly. It routes the incoming feed water through a massive heat exchanger called the economizer.
The economizer, that intercepts the 390-degree exhaust gases that are literally seconds away from venting out the chimney stack, right?
Yep. It uses that otherwise wasted thermal energy to preheat the feed water. It is wringing out every last drop of thermal potential.
And prior to the economizer, the water passes through a deaerator.
The deaerator exploits a really beautiful piece of physical chemistry. The solubility of gases in water decreases as temperature rises.
So by intentionally injecting low-pressure steam into the feed water to bring it to a violent boil.
The deaerator physically strips out the dissolved oxygen and other non-condensable gases. It brings the oxygen concentration down to a microscopic 7 parts per million.
Which, again, prevents the oxygen from chemically attacking the steel at high temperatures. The system is incredibly tightly wound. It's like it anticipates its own failures at every step.
It have to. But all of this plumbing, chemistry, and thermodynamics serves one single, highly focused purpose: feeding the turbine.
Right. The high-pressure steam, now superheated to 540 degrees Celsius, blasts into the turbine housing.
And the turbine is staged. It's divided into high, medium, and low-pressure sections.
So as the steam travels through the stages, it expands, dropping in pressure and temperature, imparting its kinetic energy against thousands of finely machined airfoil blades.
Those blades spin the central rotor shaft at exactly 3,000 RPM.
Not 2,900, not 3,100.
Exactly 3,000.
And there is a dedicated mechanical brain called the governor that acts as a throttle, right? Strictly choking or opening the steam valves to maintain that speed, regardless of how much resistance is on the shaft.
That 3,000 revolutions per minute metric is critical because it is mathematically locked to the 50 hertz alternating current frequency of the electrical grid it is supplying.
Right. If the turbine spins even slightly faster or slower, the frequency of the electricity fluctuating through the regional grid changes.
And a frequency deviation will physically destroy sensitive electronics, transformers, and industrial motors across the entire grid. The speed must be perfectly synchronized.
It is just the ultimate high-speed obstacle course. Water is dragged out of the ocean, chemically stripped of its natural identity, pushed to submarine-crushing pressures, violently boiled at 1,500 degrees,
Smashed through titanium blades at 3,000 RPM.
and then instantly chilled back into a liquid in the condenser just to do it all over again.
And that entire violently chaotic journey translates into rotational force. The turbine's massive steel shaft is directly mechanically coupled to the generator's rotor.
As it spins at 3,000 RPM, it rotates a massive electromagnet inside a stationary cylinder wrapped in miles of copper wire, the stator.
Yes, it is within that invisible magnetic flux that the roaring thermal and kinetic energy of the plant is finally converted into the silent flow of electrons.
So what does this all mean for you listening? It means the infrastructure powering our modern lives is anything but simple. When you flip that switch, you are tethering your living room to a multi-story, precisely orchestrated collision of extreme chemistry, thermodynamics, and raw mechanical violence.
It really is amazing, but it also raises an important question as we look toward the future of the grid.
What's that?
Well, we are in the midst of a massive global transition, migrating away from burning fossil fuels in favor of renewable energy sources like photovoltaics and wind.
Which is an ecological necessity.
Absolutely. But as we retire these massive spinning steel behemoths, we are removing the physical, heavy mechanical inertia that stabilizes the grid's frequency.
Oh, because the physical weight of those spinning turbines acts as an anchor.
Exactly. How do we engineer synthetic inertia to replace them? And perhaps even more urgently for arid regions, when you extinguish the massive 1,500-degree fires that boil the water.
How do you replace the millions of gallons of fresh drinking water that were, for decades, just a convenient byproduct of keeping the lights on? That is a massive challenge to leave everyone with. Something to definitely think about the next time you take a sip of water or turn on a light.